integrating the error function of sinx times the error function of cosx times sine 2x between 0 and pi over 2. So firstly, what actually is the error function? Well, it does have a very strange definition of 2 over square root pi times the integral between 0 and x of e to the minus t squared dt. But we're not actually going to be using this definition in our solution. We're actually going to be using its series expansion, which is e to the minus x squared times the sum from k equals 0 to infinity of x to the 2k plus 1 over the gamma function of k plus 3 over 2. So if we go ahead and use this series expansion in place of our error functions in our integrand, we end up with integral between 0 and pi over 2. Now the first one is the error function of sine x. So here we're going to have e to the minus sine squared x, and here our sum is going to be from m equals 0 to infinity of sine to the power of 2m plus 1 x divided by the gamma function of m plus 3 over 2. So this will be our first series. And then we multiply that by the error function of cosine x. So we end up with e to the minus cosine squared x. And this sum is going to be of n from n equals 0 to infinity of cosine to the 2n plus 1 x divided by the gamma function of n plus 3 over 2. And lastly, we have our sine 2x term. So I'm just going to expand that out as 2 sin x cos x dx. But this is already looking pretty messy, so let's try and tidy this up a bit. We have our integral from 0 to pi over 2. And here we're multiplying e to the minus sine squared x and e to the minus cosine squared x. So we put this under one power. We have e to the power of minus, and then sine squared x plus cosine squared x. And we know that sine squared x plus cosine squared x is just 1. So this here is just e to the minus 1. So now I'm going to color this first sum in red, and I'm going to color this next sum in green. So we've got this multiple of 2 from our sine 2x term, and our power for sine is going to be 2m plus 1 plus 1 from this extra sine term here. So we end up with 2m plus 2 as our power of sine. Similarly with cosine, we have 2n plus 2 as our power. And then we're going to just divide it by gamma of m plus 3 over 2 times gamma of n plus 3 over 2 dx. So now what we're going to do is we're going to swap the integral sign and the summation sign. So we have our two series on the outside. And I'll leave the e to the minus 1 term outside of that as well. Now I've just got integral between 0 and pi over 2 of 2. And I'm going to write this sine to the 2m plus 2 term as sine squared x to the power of m plus 1. And I'll do the same with the cosine term. So we have cosine squared x to the power of n plus 1. This is of course over gamma of m plus 3 over 2 and gamma of n plus 3 over 2. So now what we're going to do is we're going to do a u substitution for sine squared x. So we can say u equals sine squared x, which gives du as 2 sin x cos x dx. So we've still got e to the minus 1 on the outside. We have our sum from m equals 0 to infinity and our sum from n equals 0 to infinity. Our new bounds of integration are going to be 0 and pi over 2. This 2 here from our differential element will cancel with this 2 up here. So now we just end up with u to the power of m plus 1, which is our sine term, and our cosine squared term is going to be 1 minus u. That's the power of n plus 1. And from our differential element, we're going to have to divide by sin x cos x. So we're just going to multiply this by u to the minus a half and 1 minus u to the minus a half du. And of course, this is still divided by our gamma function of n plus 3 over 2 times our gamma function of n plus 3 over 2. I'm just going to quickly copy and paste this because it gets long writing it every time. So after simplifying our numerator, what we're going to end up getting is u to the power of n plus a half times 1 minus u to the power of n plus a half and that's divided by the gamma function of m plus 3 over 2 times the gamma function of n plus 3 over 2 du. And I realize now I actually just forgot to swap the bounds of integration to be between 0 and 1 after our substitution. So let me quickly fill that in as well. So what we might notice now is that if we just focus on the numerator of our integrand, this is actually just the beta function of m plus 3 over 2 and n plus 3 over 2. And you can use our definition of the beta function in terms of the gamma function to give us gamma of m plus 3 over 2 times gamma of n plus 3 over 2 divided by times gamma of m plus 3 over 2 plus n plus 3 over 2, which gives us m plus n plus 3. So we put this all together with our integral. We have e to the minus 1, we have a sum from m equals 0 to infinity, and our sum from n equals 0 to infinity. Now we have gamma of m plus 3 over 2 times gamma of n plus 3 over 2. And then we also have on the denominator from previously gamma of m plus 3 over 2 times gamma of n plus 3 over 2. So these end up just cancelling out, and we end up just getting this term here on the denominator, gamma of m plus n plus 3. And since we know that m plus n plus 3 is always going to be an integer, we can write this in factorial form. Sum from m equals 0 to infinity, the sum from n equals 0 to infinity, of 1 over m plus n plus 2 factorial. To evaluate the sum, the first thing that we're going to do is we're going to re-index this innermost sum. So instead of ranging from n equals 0 to infinity, we're going to go from n equals m to infinity. And to account for this, we're going to replace n with m minus m. So we end up with m plus n minus m plus 2 factorial. And as you can notice, those m's cancel out, and we just end up with n plus 2 factorial. And this is, of course, still summed over n equals 0 to infinity, with e to the minus 1 on the outside. So now what we're going to do is we're going to change the order of summation. So draw this little axis here, where the y-axis is going to be m increasing, and the x-axis is going to be n increasing. So if we just consider m being 0, we're going to start summing from n equals 0. So we have this point here at 0, then we'll say at 1, at 2, at 3, at 4, and so on. Now when m is 1, we're going to start summing from n being 1. So we end up with our first term here, and then we're going to continue going infinitely to the right. Similarly, when m is 2, we're going to start at n equals 2, and keep summing infinitely to the right. So at the moment what these sums are describing is just each of these infinite sums that keep on going to the right, grouped up like so. However, another way that we can express this same summation is instead of counting horizontally, we can instead count these vertical boxes. So you have this one vertical box at 0, we have this vertical box here at n equals 1, this vertical box at n equals 2, and then if we continue this pattern, we're going to end up getting this sort of triangular pattern. And the reason why this is useful is because instead of having an infinite sum of infinite sums, now we just have an infinite sum of these finite sums. So you can see here, we can actually write this now as the infinite sum from n equals 0 to infinity of the sum from m equals 0 to n of 1 over n plus 2 factorial. And since this is a finite sum now, we can just evaluate it normally. So we've got e to the minus 1 times the sum from n equals 0 to infinity. And this sum here is just going to evaluate to n plus 1 over n plus 2 factorial. Now if I alternatively write this numerator as n plus 2 minus 1, then we can further split up this fraction here to be n plus 2 over n plus 2 factorial minus 1 over n plus 2 factorial. And we can already simplify this first term here by cancelling out the n plus 2 on the top and bottom to leave 1 over n plus 1 factorial. And you can see here that we've just got this telescoping sum. where all these terms are going to cancel out except for the first one. So our final answer is just going to be e to the minus 1 times 1 over 1 factorial, which just gives us 1 over e. And that is our answer.